I started this series saying that relativity is about understanding how things look from different perspectives, and in particular, understanding what does and doesn't look different from different perspectives. And at this point, you'd be justified to feel like we've kind of just trashed a bunch of the foundational concepts of physical reality. We've shown how our perceptions of lengths and spatial distances, time intervals, the notion of simultaneous events, and so on, are not absolute. They're different when viewed from different moving perspectives, and so aren't universal truths. And if we can't even agree on the length of something, what can we agree on? Anyway, the point is, this relativity thing so far kind of just feels like it's leaving us hanging. I mean, all we've really got is the fact that the speed of light in a vacuum is constant from all perspectives, which, while it's true, doesn't feel nearly as helpful in describing objects and events the way that lengths and times are. Luckily, there is a version of length and time intervals that's the same from all moving perspectives, the way the speed of light is. You know how if you have a stick that's 10 meters long and you rotate it slightly and measure its length, it won't be 10 meters long in the x direction anymore? It'll be shorter? Now, if you know some math, you'll tell me it's not actually shorter, and you can still calculate its true length using the Pythagorean theorem as the square root of its horizontal length squared plus its vertical length squared. And yes, this is the case. You can use the Pythagorean theorem to calculate the true length of the stick regardless of how it's rotated. But you don't need to use the Pythagorean theorem at all. If you just rotate the stick back so that it's 100% lying in the x direction, then you just measure it as 10 meters long, and that's that. No Pythagorean theorem necessary. In some sense, this is what gives us justification to use the Pythagorean theorem to calculate the length of rotated things. Sure, it's important that the Pythagorean theorem always gives the same answer regardless of the rotation, but it's critical that it agrees with the actual length we measure when the object isn't rotated. And it turns out there's a version of the Pythagorean theorem for lengths and times in space-time that allows us to measure the true lengths and durations of things, the lengths and durations they have when they're not rotated. Except, as you know from Lorentz transformations, rotations of spacetime correspond to changes between moving perspectives. So true length and true duration in spacetime correspond to the length and duration measured when the object in question isn't moving. That is, true length and true time are those measured from the perspective of the object in question. For example, suppose I'm not moving and I have a light bulb with me which I turn off after 4 seconds. As we know, any perspective moving relative to me will say I left my light bulb on for more than 4 seconds. Like you, moving a third the speed of light to my left, will say I left it on for 4.24 seconds. That's time dilation. However, this is where the space-time Pythagorean theorem comes in. It's like the regular Pythagorean theorem, but where instead of taking the square root of the sum of the squares of the space and time intervals, you take the square root of their difference. Now, we need a quick aside here to talk about how to add and subtract space and time intervals from each other. I mean, one is in meters and the other seconds, so at first it might seem impossible to compare them to each other. But in our daily lives, we directly compare distances and times all the time. We say that the grocery store is 5 minutes away, even though what we actually mean is that it's 1 kilometer away. It just takes us 5 minutes to bike 1 kilometer, so we use that speed to convert distance to time. In special relativity, however, we convert not with bike speed, but with light speed. That is, how long it would take light to go a given distance. For example, light goes roughly 300 million meters in 1 second, so a light second is a way to compare 1 second of time with 1 meter. And a second is way bigger. So, back in our example situation where from my perspective I had my light bulb on for 4 seconds, from your perspective it was on for 4.24 seconds before I turned it off, in which time I had traveled 1.4 light seconds to your right. And the space-time version of the Pythagorean theorem simply tells you to square the time, subtract the square of the distance, measured using light seconds, and take the square root of the whole thing, which gives 4 seconds, the amount of time I had my light bulb on, from my perspective. And so we've used observations from your perspective to successfully calculate the true duration I had my light on, the duration that I, not moving, experienced. And it works for any moving reference frame. Here, from a perspective in which I'm moving 60% the speed of light to the right, I left my light bulb on for 5 seconds, during which time I moved 3 light seconds to the right. Square the time, subtract the distance squared, take the square root, and again we've got 4 seconds, the true, proper duration of time for which my light bulb was on. This all works similarly for lengths, too. Here are 2 boxes that spontaneously combust 1200 million meters apart. At least it's 1200 million meters from my perspective, in which the boxes aren't moving. from your perspective, in which the boxes and I are moving a third the speed of light to the right, the distance between the combusting boxes is now 1,273 million meters, and the time between when they spontaneously combust is no longer 0, it's 1.41 seconds, which converts, using the speed of light, to 425 million meters. And now we're ready again for the space-time Pythagorean theorem. Square the distance, subtract the square of the time, measured in meters, and take the square root of the whole thing to get, you guessed it, 1,200 million meters. Specifically, what we just did was use Lorentz-transformed observations from your perspective to calculate the true distance between the boxes from their and my perspective. And it would work from any other moving perspective, too. The bottom line is that in special relativity, while distances and time intervals are different from different perspectives, there is still an absolute sense of the true length and true duration of things that's the same from everyone's perspective. Anyone can take the distances and times as measured from their perspective and use the space-time Pythagorean theorem to calculate the distance and time experienced by the thing whose distance or time you're talking about. These true distances and times are typically called proper length and proper time, and the space-time Pythagorean theorem, because it combines intervals in space and time together, has the incredibly unimaginative name space-time interval. But don't let that get you down. Space-time intervals allow us to be self-centered and lazy, because space-time intervals allow fast-moving people to understand what life is like from my own, non-moving perspective. The astute among you may have noticed that there was some funny business going on regarding whether or not we subtracted distance from time or time from distance in the space-time interval. The short story is that it just depends on whether you're dealing with a true length or a true time. The long story is an age-old debate about what's called the signature of the metric. And if you want practice using proper time and space-time intervals to understand real-world problems, I highly recommend Brilliant.org's course on special relativity. There you can apply the ideas from this video to scenarios in the natural world where special relativity really affects outcomes, like the apparently paradoxical survival of cosmic ray muons streaming through the Earth's atmosphere. The special relativity questions on Brilliant.org are specifically designed to help you go deeper on the topics I'm including in this series, and you can get 20% off of a Brilliant subscription by going to Brilliant.org/minutephysics. Again, that's Brilliant.org/minutephysics, which gets you 20% off premium access to all of Brilliant's courses and puzzles, and lets Brilliant know you came from here.